Hi friends, welcome to our channel. Let's have a look at problem 1217, minimum cost to move chips to the same position. In this video, we are going to use parity or evenness or oddness to address this problem. So here the main requirement is that if we want to move a chip at a position I, so we can move to two positions or forward or backwards with cost 0, or move to a position 1 forward or backwards with cost 1, right? So we want to return the minimum cost needed to move all chips to the same position. So here are two examples with illustrations, and one just to give a result. So here are the constraints are the following. First, the position list, the length is bounded above by 100. And the second one is not that essential, actually. So here are the main observations are the two. First, positions of same parity need the same cost to a target position, right? And the second one is that moving from position to a target costs 0 if the position and the target have the same parity, right? And otherwise it will cost 1. For example, if you want to move a chip from position at 1 to position 3, the cost is 0. Well, if you want to move to a adjacent position of 3, so for example 2 and 4, then move 1 there would be cost 1. So with that said, let's look at the coding. So we can actually, because of these two observations, we can think of two positions, right? So an even position, right? Let's call it even position. So let's call it say 2, and odd position, let's call it 1, right? Then we want to move all the, so we want to move the chips either to this position or this position, and then we just need to make sure which one is smaller. So for P in position, so I'm going to count the difference of this P and the even position, right? So if the difference with respect to this even position is even, right? It means this is the even. If the even, actually no cost move to here. Then if you move this guy to the odd position, it will be cost 1. So otherwise, so if it were odd, then moving to this even position is going to cost 1. So let's see, even to even cost will be 0, and to odd position, the cost will also be 0. So here we should see, because it's even, right? Then if we move to odd position, the cost will be increased by 1. So otherwise, so to even cost will be incremented by 1, right? So overall, we're going to return the minimum of 2 even cost and 2 odd cost. So this is the one way of doing this problem. We specified 2 neighbor positions and use them as target position. Because of the position, because of the two observations, you can choose any even position or odd position. It does not matter. Let's first run it. Yeah, it will pass. Yeah, it passed all the cases. So actually, this code is sort of redundant. Let me consider this. So here in this solution, we used specific odd and even positions. Actually, this is not necessary, right? So here we can think of moving all the positions to an even position or odd position, right? So we just need to check the parity or even oddness of the position, right? Then we just return the smaller of the even odd count. So here, let's see, even count, that's odd count, so it will be 0. And then for position, in position, right? So if P modulo 2 is 0, this means that this P is at even position. So if it, let's first make sure the even count is incremented by 1. Otherwise, so the odd count is incremented by 1. So what we want to return actually is the minimum of even count and odd count. So the interpretation is like this. So if the even count is larger, right? So then we want to move all the odd positions to this even position. Otherwise, if the odd count is larger, then we move every position, every chips to the odd position. So this will be the interpretation of this code. Now let me run it. Yeah, it passes all the test cases. So with that said, I guess that's it for the current video. Thank you for watching.